Here's a quick intro to improper integrals. So think about this. We can ask the question, hey, what is the signed area of the curve from 0 to infinity of e to the negative x dx? So think about that. The curve e to the x looks like that. The curve e to the negative x looks like that. And right, the signed area under the curve is that, but it just goes on forever. So how do you ask that? Well, we ask it the same way we ask the question about a whole lot of questions in calculus. We say, well, how could you get close to that? Well, what if you didn't go 0 out to infinity? What if you went just 0 out to some number b? And then, that, regardless of what b is, you could ask that. And if you wanted to get closer, let's actually ask what happens as b goes to infinity. Well, this integral is just fine. And so in a lot of ways, the trick to improper integrals is you wait to apply the limit until the last possible moment, and then you see if that limit goes to infinity or whether that limit goes to a finite number. So let's leave our limit alone until the last possible moment. This integral, the integral of e to the negative x is negative e to the negative x, right? Evaluated from 0 to b. Don't apply that limit. You can wait still longer. So what is that? That's negative e to the negative b minus negative e to the 0, right? Well, now I can actually apply that limit as b goes to infinity. Maybe I should rewrite that before I do that, just so it's a little clear what's happening. What is e to the negative b? That's 1 over e to the b plus 1. Well, what happens as b goes to infinity here? That's 1 over infinity, or 0 plus 1, or 1. And so that signed area under the curve is 1 as b goes out to infinity. So we can actually ask, even though the width is infinite, because it gets so small, the area under that curve is 1. Well, this, obviously your x value, so it's infinitely long. What about infinitely high? That's kind of the other category that seems like it's improper to think about. Let's think about this one. You remember the graph of natural log of x looks like that. At 1, it's 0, right? Natural log of 1 is 0, but it has a vertical asymptote at x equals 0, and of course it's not defined to the left of that. So I could ask, hey, here's an area, it's improper. It's not even defined at that point, right? So you could say, hey, what's the integral from 0 to 1 of natural log of x dx? But it's sort of like, well, this isn't defined there. So, well, but I'll tell you what. What if I just had sort of an a there and I got really close? What if I just integrated from a pretty small a up to 1? That would get you close, right? And then, well, as long as you can tell me what happens as a goes to 0 from the positive side. You can't just leave that unsigned because we can't go, a normal limit allows the a to come from the positive or the negative side. And a negative value isn't defined at all. But coming from the positive side, I can ask that. Now, again, same not so secret principle. I'm going to wait my limit until I have totally worked with this. What was the integral of the natural log? Well, you may remember from integration by parts that we actually did this one, right? I'll just sort of do an aside refresher over here. U was natural log of x, dv was just dx, right? So that du could be 1 over x, and v was equal to x, and so we did that, right? And we did x natural log of x plus, and then you remember how this worked. It's minus the integral of v du, those ones canceled, so you actually have x, and then it's x natural log of x minus x plus c, right? And if the litmus test for whether that's right is take the derivative of this, right? Derivative of this using the product rule is natural log of x times 1 plus x times 1 over x, that's 1, minus 1. So you can sort of see why that would be the integral. So I'm going to just use that fact over here. all evaluated from a to 1. Now, the limit, I'm going to, wait, resist the urge to plug in that limit. Okay, so what is this? This is 1 times 0 minus 1 minus a times the natural log of a minus a, right? Okay, so what's going to happen there? Excuse me. Well, I guess you could factor out an a if you wanted to. Limit as a goes to 0 from the positive side of minus 1 minus a times natural log of a minus 1. Okay, that minus 1 being on the outside. So what happens there? If you were applying that limit, can you see that this is an indeterminate form? This is that negative 1, by the way, just sort of comes out, right? The limit isn't affected there. This right here is 0 times negative infinity. That's an indeterminate form. How do we deal with that indeterminate form? Well, we can actually put that in the denominator. So let's have minus the limit as a goes to 0 from the positive side of the natural log of a minus 1 over 1 over a. Now 1 over a is a, but this is a different indeterminate form. This right here is negative infinity. Now this is infinity. That's an indeterminate form I can use Hospitals on. Do you remember Hospitals? Hopefully you do. Hospital says, and I'm going to write an LH just so I remember, this is not equal in the sense that it's an algebraic manipulation, but Hospital says if it's an indeterminate form, infinity over infinity or 0 over 0, I can take the derivative of the numerator. The derivative of natural log of a is 1 over a. The derivative of negative 1 is 0, by the way. The derivative of 1 over a, that's, or you could say a to the negative 1, is negative 1 over a squared, right? Well, what is that? That's negative 1 minus the limit as a goes to negative infinity. Take the reciprocal of that, that's negative a. What is that? That's 0, so negative 1 plus 0 is negative 1. That area, that signed area, is negative 1.